A couple in March, I was at Santa Fe Institute and had a fantastic time. So whenever you have time or invited, absolutely go. And one of the big surprises was to meet Sydney sit there. And I'm a psychologist and since working in the field of statistical physics, but I had many interesting meetings and conversations with him. And next week we are teaching together in Vienna. And for me, that was a good reason to ask him to come a bit earlier to Amsterdam. And we already met some people at the physics department, and you've been in my lab. And I'm very happy to have you here talking today about one of your lines of research that I think will everybody like to hear more about. So, the floor is yours. Thank you.
Okay, well, thank you for having me. It's been very nice to be here. And I guess what I would say for the people who are out there in Zoom land, I mean, just if you have a question, please just shout it out. I mean, no reason to be very formal. So also, this is a kind of diverse audience for me, so I'm not exactly sure how to present, what level to present. So if something isn't clear, just ask. So the work I'm going to present to you is over a long period of time, and it was in collaboration with Elie Ben-Naim, a former PhD student, Deepak Bhatt, who was a recent postdoc, my longtime collaborator, Paul Kapitsky, and also another former PhD student, Federico Vasquez. And then always you have to say support from the National Science Foundation. So anyway, now this isn't working. Oh no, here it is, okay. So here are the two basic questions that I want to organize this talk about, which is that, over the past maybe 30 or 40 years, a number of statistical physicists have applied very simple mathematical modeling that comes from mathematics to understand social dynamics. And a lot of the effort has been focused on understanding the approach to consensus. But we know from our everyday experience that consensus is really hard to achieve. And so the two questions I want to address here is that if people are reasonable, then why is consensus hard to reach? And also, if people are reasonable, which we hope they are, then why does it seem that societies are falling apart? I really won't answer these from a sociological perspective, but just to give you some sense of some simple-minded models that don't reach consensus and maybe provide a way to understand the answers to these questions. So, first of all, from the perspective of statistical physics, this is how most physicists would try to model societies. So here's a bunch of real people. Everybody's very different, different sexes, different races, different, incomes. There's all kinds of features to them. But it's almost like the same as there's a standard joke about a theoretical physicist who's trying to increase milk production at a farm, and he studies the problem for a year, and they begin this presentation, consider a spherical cow. And so here, the analog of consider a spherical cow is we consider people as like a fused state, system. And so in this particular instance, we might imagine they're like spin up or spin down. They're either Democrat, Republican, positive, negative, and that there's some very local interactions among some people, and it's going to be the locality of the interactions and the simplicity of the states of each individual that allow us to apply tools in theoretical physics to try and understand how a society might evolve. And again, when I say how a society might evolve, I really mean like a toy model of a theoretical physicist, how a society might evolve. So it's not real societal evolution. So now that you sort of see the kind of picture I have in mind, I'm always doing the spherical cow approximation. We might ask, like, what are some natural mechanisms that you would not, for which you would not reach consensus? Because in the model of, like this sort of spin up, spin down model, if there is an interaction that people tend to, when I talk to Han, we get closer to each other in opinion. So if that's the only interaction, that should suggest that you reach consensus. So how can you not reach consensus, even if you have more or less positive interactions among people? And so here's sort of a grab bag of possibilities. One is that, I've only met Han just this year. And so like for the previous 70 years, I didn't know who he was. And so we didn't communicate very often. Another feature is that people are all different. And in fact, in most physics modeling, so this is now being self-critical, most of the modeling that I've done and other people have done have all been based on people who are all identical, which is pretty stupid. Then there's also the notion of competing echo chambers, that I might watch CNN News and you might watch Fox News. And so we have different notions of reality because what we hear from the outside media can be very different. And then, you can think of your own favorite example. And so in this talk, I'm now going to present some models that incorporate each of these features and give you a sense of like, what's the range of possibilities. So the models that I'm going to discuss is, first of all, a voter model, but you have, instead of 2 states, 3 states with a possibility of incompatibility if the 2 states are too far apart. I'll also discuss what's called the bounded compromise or bounded confidence model. And I'll show you some very, I think, beautiful results for what happens there and some possible applications. I'll say a few words about the Axelrod model. I'm just going to define it so you know what it is. It turns out that mathematically, that's probably the most subtle of the models that I've ever worked on. So I'm not going to show any results, but just give you a sense of what the model is. And finally, I'll talk about the good old voter model in the presence of competing externalities. So that's the goal. All right, so let me begin just by talking about the voter model. So in some sense, this is the fruit fly of social dynamics. It's like the simplest model, and it's very soluble, and everything is known about it that can't be known. And the other thing which is kind of amazing to me is that it was introduced by mathematicians, and the physicists took it over. Usually it's the other way around. Physicists dream up some model, and then the mathematicians solve everything. But this one was just the opposite. So here is the good old voter model. So we imagine that we have some kind of a graph, a static graph, like it could be a lattice or some arbitrary graph. And in each node of the graph, there is a 2-state or binary variable, which is the state of a voter. And it can either be, here I've represented geometrically, spin up and spin down. So here on the square lattice, I have a central voter in red, and it's surrounded by 3 up neighbors and 1 down neighbor. And the way that the voter model works is as simple as possible, which is you start by, populating your graph. You pick a random voter. So in this particular case, I picked the red guy in the center. The red guy has no self-confidence. And so what I would do if I'm a voter with no self-confidence, I'd look around and say, I pick Han. And who did you vote for in the last election? You say Donald Trump. I say, Donald Trump. What a good idea. And so I just adopt the state of a random neighbor. So in this particular case, as I've shown it, no self-confidence, you pick the state of a random neighbor. So in this example, you see 3/4 of my neighbors are up, 1/4 are down. So 3/4 of the time I pick one of the up neighbors and nothing happens. 1/4 of the time I pick a down neighbor and I change my state. And you just do this update step over and over again until a finite system necessarily reaches consensus. It's easy to show that there is no other state, long-time state of the system. So the other thing that I just wanted to emphasize here is that this particular rule, the rate at which you flip is proportional to the number of disagreeing neighbors. And so this is what's called proportional rule. It's different than the Ising model, where the Ising model is pure majority rule. In the Ising model, if I have 3/4 that spins up, then for sure I always take up. I always go with the majority. Proportional rule turns out to be simpler mathematically, and that's basically why the voter model is solvable in all dimensions, whereas the kinetic Ising model is only solvable in 1 dimension. Anyway, so we repeat these steps over and over again, picking a random voter, letting it update, and it reaches consensus. So let me now sort of summarize 30 years of work very quickly, which is the 2 basic properties of the voter model. Okay.
Trying to get rid of the noise.
Yeah, I'm sorry.
That's okay.
It's really disruptive. I can really ask them to stop.
Okay.
Sorry.
That's okay. So 1 basic property is what's called the consensus probability. So suppose that you begin with a fraction row of your spins or your voters in the spin up state. And then you can ask, what is the probability, since a system necessarily reaches consensus, what is the probability end up with positive consensus when the initial density of spin upvoters is rho? So that's, okay, so I'm just stating it again. So it turns out that this result is actually very trivial to prove what it is, because first of all, I mean, in principle, what you have to do if you're doing a simulation, you start, say, with 2/3 your voters up, you do lots of simulations, you see how many end up with all plus, how many end up with all minus. And if you do such a simulation, you'll find that it's actually 2/3. And it turns out the reason why that happens is that this process in the mathematics literature is what's known as a martingale. And a martingale is a fancy word for a game which is always fair. So the point is that if you look at any individual spin, the average is conserved at every single step. And because the average is conserved, if you start with a density rho initially, at the final time, there's only two possibilities. You either have everybody spin up or everybody spin down, and the probability of reaching spin up is this E of rho. And so the average density initially is rho. The final density has to be equal to rho, which is the probability of reaching spin up times 1, plus the probability of reaching spin down, which or zero spin, 0 times 1 minus the probability of reaching spin up. And if, I mean, I'm sort of stumbling over the words, but the point is it's just E of rho is equal to rho. So it's as simple can be.
So the 2/3 is in all dimensions.
Yes, it doesn't depend on the, well, actually, I should say one more thing, which is that this applies if you're dealing with a graph that is degree regular, everybody has the same number of neighbors, this is true.
Yeah, sure.
But if people have different fraction neighbors, then it's
not true.
It's not true anymore,
sure.
It's very different.
Sure.
Yeah, and actually different for an interesting reason. So in fact, if you play the voter model on a complex network, it's a very different model, it's very beautiful, and that's a whole nother talk. The other thing is the consensus time. How long does it take to reach consensus, either all spins up or all spins down, starting from a fraction rho? So I'm not going to show this now, but I'm going to come to it later in the talk when I will discuss like a voter model in the presence of competing externalities. But let me just tell you what the results are. So it depends only on the spatial dimension. And in a lot of these problems, the spatial dimension is kind of like an important parameter from the perspective of statistical physics. So in 2 dimensions, above 2 dimensions, there's enough neighbors around that basically you can say that the local neighborhood and the average neighborhood of the entire system more or less are the same thing. And because of that fact, one can apply a mean field approximation, and then it's easy to show that the consensus time scales linearly in the number of spins. Now, what I mean by consensus time is that, you know, it's not like each individual update step is a time of 1. It's just that when every spin has been attempted once to flip, that would correspond to a time update of 1. So it's n squared microscopic time updates, but n, you know, the physical time is scaling like n. In 1 dimension, it's also easy to show that the mean time to reach consensus scales at n squared. And then in 2 dimensions, which is the boundary between the mean field behavior and 1-dimensional behavior, one typically gets logarithmic corrections, and that's in fact what one sees. So this is kind of just a background into what I want to go into now, which is discussing extensions of the voter model that lead to either diversity of opinions or actually long-term polarization.
Can I just ask, that's a basic question. So isn't the statement that the 2/3 statement, isn't it just related to the fact that a single spin, the neighbors of a single spin, there's just initial stated, there's just one more spin in one direction than in all of the other ones?
No, I mean, I guess, no,
on average, is that the same?
No, again, I would say that the mechanism is just that you know, when you like average over, you know, you take a given spin and just say, well, what can happen to it? Either goes, you know, if it's down, it can go up, it can go down. And that fact just says that the average spin is conserved. Simple as that. So just average spin is conserved. And so if it's conserved in a single step, it's conserved throughout the entire dynamics. And that's
sure.
Yeah.
Okay.
Yeah. All right. So the first example is 3 voting states. So let's imagine now that instead of having just two states, that we have three. And so we can think of this as extremist left, centrist, and extremist right. And again, if everybody interacted with everybody else so that any pair of opinion states could influence each other, that would be just like, it's like a Potts model in a spin language. It's a slightly more complicated version of the voter model, but would have the same voter dynamics. But now I'm going to have one more twist to this, which is the following. So again, I'm doing the voter model update. I pick a voter at random. I mean, I endow my lattice with, or my graph with voters of these three states. I pick a voter at random, and then I assume the state of a neighbor, but only if it's compatible. So what I mean here is that if I am a centrist, I'm very compatible with everybody, so I can talk to a right-wing activist, I can talk to a left-wing activist, and we can discuss and have a productive discussion. One of us might change your opinion. But if I'm a right-wing activist and you're a left-wing activist, we have nothing to talk about. So we just say, screw you, and we don't even interact. So that's really all there is to the model, is that you just assume the state of a compatible neighbor and you repeat ad infinitum. And now there's a new feature that the long-time state could either be consensus, or if you have somehow gotten rid of all the centrists and you have a country of Trumpists and a country of, I don't know who's the most leftist American politician, but you have Trumpists and everybody else, they have nothing to say to each other, and then you're stuck. There's no evolution of the system. So again, centrist and leftist, whoops, I don't touch that. Okay, centrists and leftists, they can equally likely go to both centrists or both leftists. Centrists and rightists can go to two rightists or centrists, but two incompatible neighbors, nothing can happen. And here the probability of each of these microscopic events, at least in a mean field description, and so I'm only going to do this in a mean field description because low dimension is much harder still. But the point is that in this mean field description, the probability of picking a leftist and a centrist is proportional to the density of each. And so that's why it happens with probability rho zero, the density of centrist, times rho minus the density of leftist. And so with these different probabilities, these events can occur, and you do this over and over again and sees what happens. So let's see what happens. And so in this case, we have three states, three densities. And so we have the state space is the density of zeros, pluses, and minuses. So it's a three-dimensional state space. But there's also the constraint that the density of zeros, pluses, and minuses have to add to one. And so that constraint plane is like some 45-degree plane, and the intersection between the three-dimensional state space and this plane gives this composition triangle. So for example, here, this is all centrists, all leftists, all rightists. And so we start somewhere on the plane with some initial condition. And then according to the voter model dynamics, some evolution occurs. And so here I'm showing two different types of trajectories. One is this purple trajectory where you start with all three species represented, and somehow all the centrists have been removed from the system, and you fall onto this line. And once you reach this line, this is a frozen state because you have plus, leftists and rightists, they don't talk to each other. So whenever you reach this red line, you stay there forever. On the other hand, if you reach this line, that means you've gotten rid of all extremists of one persuasion. And now you just have the good old two-state voter model with either centrist and either all the rest of the population, either leftist or rightist. And so you'll necessarily reach consensus. So the new feature of this model is that you don't necessarily reach consensus. You can reach either the frozen line or the different consensus states. And one could ask, what is the probability of reaching either of these states? So let me show you a little bit of the mathematics that underlies this. Let me call capital F the probability to reach a frozen state starting from some particular initial state, rho minus rho plus. Since the densities add up to 1, rho 0 is 1 minus rho minus rho plus. So I'm not writing the third argument because it's a two-dimensional state space. So we can ask, what is this probability? And it turns out that there is a very nice way of thinking about this using techniques of first passage processes. And so the idea here is that one writes what's called a backward Kolmogorov equation. This is a mouthful of what the words are, but the physical meaning of this equation is very simple, which is that if I start in a particular state, well, after one interaction, my in state space, it moves somewhere else in state space. But then the process starts all over again, but with a different initial condition. So the probability of reaching a particular frozen state starting from rho plus rho minus, well, if, so let me, I guess, put the equation down. So the point is that with a probability rho 0, rho minus, I have an interaction between a centrist and a leftist. And when I do that, either the centrist becomes a leftist or the leftist becomes a centrist. And so the density of the leftist will either increase by some amount or decrease by some amount. This delta here is basically 1 over the number, 1 over the population size. And so with this probability, I start here and I'm trying to ask, what's the probability to reach a frozen state? Well, after one event, I can either go here and then I have the same process starting over again with a different initial state, or I could have gone over here and I have the same process with a new initial condition. And that's what's encapsulated by this equation. So either the first argument changes or the second argument changes, if I have an interaction between a centrist and a rightist. And then this is the complementary probability that I pick a leftist and a rightist, and then nothing happens. So that's the equation we have to solve. So, that doesn't look like a very easy equation to solve. And in fact, it's not very easy to solve. It took us like 6 months to figure out how to solve it, but it can be solved. And so if you do all of that work, so it turns out in the continuous limit, which is the simplest case to look at, you just take the limit where delta goes to 0. One writes a differential equation. One sees it kind of looks like the Laplace equation of electrostatics, but it has sort of asymmetry to it. And so one has to do a little bit of work here. So that work is represented by the meat grinder, and you grind away. And in the end, you find an analytic expression for this exit probability as in terms of these are the associated Legendre functions. So it turns out one has to do some mapping to quantum mechanics. Anyway, you do all of that stuff, and that's the answer. And here's like the specific case in the symmetrical limit where the fraction of extremists of either persuasion are equal. And in that case, it looks much simpler.
So this probability of reaching the frozen state only depends on densities and not on how the photons are distributed in your lattice.
Well, the thing is that this is in the mean field limit.
Mean field.
Right. Yeah. So in a lattice situation, it's much harder still. Anyway, so the main import that comes from this is that we can now draw a phase diagram. And so here is my composition triangle. And each one of these little regions here corresponds to the probability of reaching that particular state with a probability larger than 50%. So there's a fairly large region where if I start somewhere here, there's a more than 50% chance I end up with consensus of centrists. Here, a more than 50% chance of ending in the frozen final state. And in these tiny little regions here, there's a probability of reaching either plus consensus or minus consensus. And that comes out from this, analytical expression. And let's see what else I can say about this. And so here again was my phase diagram. And here what I'm plotting as a function of the density of centrists is the probability of reaching a frozen final state, which goes to 0 if there's no centrist, because then there's no chance of reaching the frozen final state. This is the probability of reaching 0 consensus. Oh, I touched it. And these curves here are the probability of reaching either minus consensus or plus consensus. And that all comes out from that Legendre function solution.
So the frozen state is the biggest area in that figure?
Here, this thing here.
Yeah. And it's the biggest, like it's more likely that you end up in the frozen state.
Correct. Yeah. Yes. So, I mean, the point here, which is like obvious, is that if you have extremism, it promotes deadlock. The more extremists you have in society, the less likely anything productive is going to happen. Okay. So let me now talk about the bounded confidence or bounded compromise model, because this is an exceedingly simple model and it has some incredibly beautiful results associated with it. And so what is the bounded compromise model? So the idea here is that we have people now with continuous opinions. I mean, one feature that you might find not very fun about the voter model is that the opinion states are discrete. That's not terribly realistic. So the bounded compromise models, we assume that people have a one-dimensional opinion coordinate that can be continuous. And if two people have an opinion difference, which is within a confidence limit or a compromise limit of 1, then what they do is they compromise. So this is what happens. However, if two people's opinions are outside of this confidence limit, then nothing happens. And that's all there is to the model. And again, one can play this on a finite dimensional lattice or in the mean field limit, but let me just focus on the mean field limit because it's both simpler and for modern society, since it's very easy to communicate with almost everybody, it's not an unreasonable kind of assumption. Now, one point I want to make about this is it turns out that this picture of taking two particles and averaging their coordinate, this is what happens if you had a mechanical system of particles moving around in a lattice, moving around in space, and when two particles meet, they just stick together irreversibly. So it turns out that some of the mathematics associated with understanding the dynamics of a gas of completely inelastic to scattering particles can be used to understand the dynamics of this model. And so the thing is that what a lot of people have done sort of simulations of this process. And the problem with the simulations of this process is that as people get closer and closer together, you're doing lots of events where someone with opinion 1.001 and someone with opinion 1.00001 are averaging, and sort of you're spending a lot of time doing events that basically don't do very much. So it turns out that by treating this from a more mechanistic perspective, one can get much better information and much easier. So here, the fundamental quantity is the probability distribution that, or the opinion distribution. So the probability that an agent has opinion X at time t. And our fundamental parameter is the initial diversity. So we have this range 1. If everybody's within the range 1, then everybody will compromise, and you end up with consensus. But if some people are outside this range, then we'll see that there's some very interesting things that can happen. So again, because I work in non-equilibrium stat mech, and we always like to look for connections across fields, and this connection with sort of the hydrodynamics of an inelastically scattering gas was very convenient. So what one writes down here is basically what's known as a Boltzmann transport equation, which is how the probability distribution evolves as a function of time. And this equation looks kind of formidable because it's an integral differential equation, but its physical meaning is quite simple. So how does the probability distribution change? The way it changes, I have to take two people. So that's why there's two probabilities, the probability that someone has opinion X1 and someone has opinion X2. And there's two possibilities that can occur. One is that if two people with opinion X1 and X2 such that X1 plus X2 over 2 equals X, then you gain somebody of opinion X. And so there's a gain term, because it comes with a plus sign, a gain term when X is equal to the average of the opinions. And then there's a loss term, because if somebody interacts, then you lose somebody who had that opinion because it goes to some other. And so this sort of competing gain term and loss term, and the loss term is because when you interact, you lose your opinion, and when you gain because you create somebody of opinion X. This looks like a Boltzmann transport equation for kinetic properties of like a gas particle. And it turns out then one can use techniques from kinetic theory to solve this equation or get information about this equation. But the other feature about it, which is also nice, is that instead of simulating individual particles and doing lots of little dorky events that are like infinitesimal, you actually integrate this equation in time and you get much better information very quickly. So let me just give you a sense of what happens. Here's one particular example where I'm starting with more or less a uniform distribution between -4 and +4. And then if we integrate that integral differential equation, one sees that, people here kind of form a cluster, and people here form a cluster, and everybody here is kind of not, they're sometimes moving towards the center, further away. But eventually, one ends up with a very beautiful picture in which you have nucleation of extremists and nucleation of sort of center left and center right. And the thing is that this detail can be only found in an unambiguous way by doing this integration of the master equation. And so now let me use that fact to actually look at the full fragmentation sequence. So basically, this is a phase diagram of the process as a function of the initial diversity of the population. So initially, I'm going to begin with a symmetric distribution of people, between minus delta and plus delta, the diversity, and then we're going to see like what is the final state of the system. So if the diversity is less than 1, then we saw that we'll necessarily reach consensus. And as soon as the diversity reaches 1, there is a fragmentation sequence in which most people, go to the consensus in the middle, but like the people right at the edge, they form their own little cluster and they make a small cluster of extremists to the left or extremists to the right. But as you increase the diversity, something else happens, which is that at some point, the centrists kind of are wiped out, and what's left are kind of center left and center right, and the extreme left and right. And then if you continue making the initial population gradually more diverse, there is this whole sequence of bifurcations that happens in a self-similar way. And the only way you can really see this in an unambiguous way is by this integration of the master equation for the probability distribution. And so it looks like this. So very pretty looking picture. And there's a sequence where the centrists are here and then they disappear, but then as you make it more diverse, then there's always people like finding the new enclave far away from everybody else. And then the picture I like to make of this is that if you then look at Germany, 7 parties in parliament. So in some sense, it's a measure of like how diverse is the population. And the most argumentative country in the entire world, I mean, does anybody have a guess what it is? Most argumentative democracy? Israel.
No.
13 parties in the Knesset. And the thing is, when I gave this talk 10 years ago, Germany was 5 parties. Israel was 9 parties. And so it's just going to the right. And then let me just say something about my own home country.
Can I just ask something
please.
in that model? So the idea of this is just that, yeah, you have this gas of interacting stuff, and opinion is sort of reached by the interactions of these molecules. That's the idea. Proximity, and that's it.
Proximity in opinion space.
Yeah.
Not proximity in physical space.
No, sure. Proximity in opinion space.
Right. Okay. All right. So, anyways, my home country, Canada. And so, for those of you who don't know Canada, let me tell you, Canada 101. Typically, there were 3 major parties. There's NDP, New Democratic Party, which is very leftist. There was the Liberals, which is kind of like center left. And then this thing, which is an oxymoron, Progressive Conservative Party. And over the years, these 3 parties are always competing. The NDP have never been in power, and liberals and conservatives have been trading power. And if you look at the years here, this is 1980s. The year is the Reagan. And then the Reagan years, like Canada kind of follows the United States. So in Canada, we had a prime minister named Brian Mulroney, who was a blood brother of Ronald Reagan. They liked each other. They hosted each other at summits. They would quote poetry of Canada and the US to each other, lousy poetry. But anyways, and social credit, forget about that. Anyway, so this is the landscape up till 1988, when the conservatives had a huge majority, like a 2-to-1 majority. And then I think in the history of any kind of a Democratic Party, the result of the 1993 election was truly mind-boggling. It was this. NDP was wiped off the map. Liberals had this huge majority. Progressive Conservative just disappeared. Like, this is a major party. It just went away. And then one sees also the beginning of a party here called Parti Québécois, which basically all they want to do is separate from Canada. There was no other point of them, except they want to separate from Canada. And then there was this Reform Canadian Alliance Party, which is really right wing. So, it's like the country was splitting apart. And, I'd say that this event has sort of continued to this day. All right, so let me tell you about the Axelrod model. Here, I'm going to not show any detailed results. I just want to tell you what the model is, because it's such a beautiful model and so interesting, and it's really poorly understood. I think it's really an open area. And so here is the Axelrod model, which was like an attempt to try and be a little bit more realistic in like how people's opinions are constructed and how they might evolve. So instead of saying I'm a two-state person, I'm either spin up or spin down, I'm actually more, I hope I'm more interesting than that. I live in some place, I have a certain set of politics, there's certain recreational activities I have. I like to eat, and so there's certain types of food I might eat, and then I have a car. What kind of car do I drive? And so let's imagine that you characterize people not by just are you spin up or spin down, but how many different features. And so one of the parameters in the Axelrod model is the number of features you characterize a person by. So here I have 5 features. But then for each feature, there is a menu of possibilities. So for example, if I'm talking about cuisine, I could be a meat eater, I could be vegetarian, I could be vegan, I could be dieting all the time, or I could decide I should fast weekly because that's healthy or whatever. So there's a whole range of possibilities, so that for each one of these F features, there's a certain number of traits, cute traits. And so the Axelrod model is characterized by the number of features and the number of traits. And so you might expect that if there's lots of features and lots of traits, then the society is kind of like a cacophony of everybody with very different opinions. And then the question is, does this system reach consensus? And the feature about the Axelrod model, which is really quite beautiful, is that in the Axelrod model itself, the interaction is purely ferromagnetic in the sense that everybody tries to move closer to each other. So let me show you what the interaction is. So, for example, here's me. Well, I don't live in an apartment, but politics, apathetic, skiing. Well, actually, I haven't skied in 30 years, but I like skiing. Okay, I don't eat meat, so this isn't me, and I don't drive a Ford. So this is some random person. But the point here is that suppose you take the rules of the Axelrod models. You take 2 people at random. Here is a set of traits of one person. And here is some, okay, so that's you eat. I don't know if you drive a Ford, but you meet me, like I commute by bicycle, I'm a vegetarian, I like running, I'm apathetic, I have a house in the city. Okay, this is me. And so what we do now is say, okay, here's my traits, here are your traits, but we're both apathetic politically. So we have something to talk about. We both don't care about politics. And because of that, we have a discussion about anything and everything. And so along the way, I convince you to become a vegetarian. But it's only because we share one trait that we can even begin to speak. And so this is the dynamics of the Axelrod model. You have your 2 people, you see if they have any traits in common with a rate proportional to the number of common traits that they share. They pick another trait and one person moves closer. And so the question is, do you reach consensus or do you reach a state of cultural fragmentation? And the interesting feature about the Axelrod model is that indeed there is a phase transition between cultural fragmentation and consensus as a function. What's happening now? It looks like I've lost my Zoom.
Oh. Maybe, yeah, you lost it indeed. You disappeared.
Should I try to?
Actually,
We can still hear you, or?
yes.
The slides are not on.
Yeah, should I try to? Oh wait a second, I lost my
Maybe there was the connection, right?
yeah, because I'm an edgy roam. Technical difficulties, we'll try and solve it. Yeah, so.
Do you have it back, everyone?
Now, well, now it seems that, well, it's coming back, I think. Net connection failed.
You know,
Okay, now it's back. So let me try to relaunch. Okay, so it looks like I'm back again. Got it. And I want to start video.
no.
No, I don't want to start video.
You want to share screen.
Share screen, right, okay. Here it is. Share screen. And where was my? No, preview. Where's my, oh, Keynote died. No, here, a minute. No, where's Keynote now? Why does it not show Keynote?
That's right.
Well, yeah, sure.
Weird.
Yeah, it's funny, like it's not one of the choices available.
Okay.
Oh, here, okay. All right. So are we back?
Yes.
Out there in Zoom land?
Yes.
How do you play it? I don't know, Keynote.
Okay. Let's move this out of the way.
Yeah, you should go to full screen, not right? Okay.
Okay, so are we back now?
Yes.
Okay.
Yes.
Very good. Okay, so anyways, and here I just have to move all these other windows out of the way of my screen because they're blocking my view. Okay, so anyways, here is the results of the Axelrod model, and it turns out there's a very beautiful paper from more than 20 years ago by Castellano, Marsili, and Vespignani, who investigated this by simulation. And I'm just showing these because the simulations are so bizarre and it's really not very well understood. So the first point is this notion of the transition between unanimity and cultural fragmentation. And so here is simulations for a model where you have 10 features, and forget, I mean, it doesn't really matter about the system size, that's a secondary thing. But the point is that there's also the number of traits per feature. And one sees here that as a function, if you fix the number of features and then increase the number of traits, there's a transition from a state where you have unanimity to cultural fragmentation for large Q. And so that's the main result that happens here. It turns out that
Those are like 400 features. Is that really the numbers?
yes, I mean, not number of features, number of traits per feature. F is here 10 features,
okay.
a number of different traits. The main point here is that it looks as the system size gets large and it becomes a first order phase transition. There's a sudden jump between consensus and fragmentation at a critical value in Q. And in the case where there's only 2 features, it appears to be a second order transition. So that's kind of weird. But even more weird is this, and this is the plot that I just wanted to like have you marvel over, because it's not even, they don't even mention it in their paper. They just say, here's a simulation. And so this is the fraction of active links. So the point is that if I share a common trait with Han, then there's a possibility of an active link between us. But you know, among a bunch of other people, I might have no common features with you or with you. And so we just don't even talk to each other. And then the question is, how many active links are there as a function of time? And again, this is showing for 10 features and changing the number of traits. And notice, first of all, the time scale. It's like this is a logarithmic time scale here. So there's incredibly long time dynamics. So it's like somehow the society can get stuck in a situation for a long time. And then there's a huge change in the number of active links. And the other point I want to emphasize is the non-monotonicity of this. Like who ordered that? The number of active links goes down, it goes up again, it goes down with huge different separation of timescales here. So this feature, which I think is actually something that does happen in real societies, if something seems latent for a long time and then it suddenly emerges, I think this is really kind of an interesting aspect. And so I just wanted to more or less advertise it because I think it's a relatively unknown. Okay, so the last part of my talk is the role of competing externalities. And this is much more recent work that I did with my postdoc Deepak Bhatt at the Santa Fe Institute. And here we're just doing the simplest thing we could possibly imagine, which is ask, suppose we have the good old voter model, but in addition to that, there are competing news sources. So in the United States, you may know that there are these, there's this sort of right-wing media and there's left-wing media, and they seem to have completely different realities. If you watch Fox News, you think the sky is blue. If you watch CNN, you think the sky is green, and there's just sort of no commonality between them. So we wanted to try and like implement that in the simplest setting of the voter model. And so here's the setting we have in mind. So this is meant to represent a complete graph. So we're doing this in the mean field limit where everybody interacts with everybody else equally likely, but some fraction of the population watches CNN news, which is some center left, I guess. And some fraction watches Fox News, and I don't know what you would call that, if it's a news source or a propaganda source, but certainly on the right. And then the question is, what is the evolution of the population or the opinions in a situation like this? And so what I mean by Fox News or a news source is that this is always having the plus opinion. Nobody can influence Fox News, it's always plus. It's always broadcasting change to the plus opinion to everybody. And CNN similarly. And then people in the middle, they evolve according to this guy interacts with this guy and that guy and somebody else over here. And so he looks at the opinions of the three people he's looking at, plus he watches CNN news. So he's watching CNN news, he's talking to three of you people, and based on that, he picks one of those neighbors at random and adopts the state of that neighbor. So it's just the good old voter model, but with the notion that two of the voters, CNN and Fox, are fixed for all time. And then we can ask what happens. Now, it turns out that there is another parameter that gets introduced into this model, which is what I call the propensity to actually look at the news source compared to one of your neighbors. So, this guy, for example, has 4 neighbors, 3 people, and 1 news source. And the thing is, you can say, well, how many hours of TV do you watch a day, which will be sort of proportional to this parameter P. If you're only watching Fox News all the time, then your eyes get glassy-eyed and you just follow Fox News. But if you watch it maybe 10 minutes a day and then talk to 3 of you guys, well, then you have a chance of being influenced by somebody else. So that is characterized by this news propensity P. And so you'll either listen to the news or listen to a neighbor with a complementary probability. And then we just run the voter model on that. And it turns out that there's now not just 2 basic properties, but 3 basic properties of this voter model. So there's first of all this question of like what I call the exit probability or the probability of reaching consensus, let's say all plus. There is a time to reach consensus, but now there's a new time in the problem because if you start close to consensus, then the system, because CNN and Fox are trying to promulgate different opinions, you can reach a state which we call the maximally polarized state, 50-50 polarization. So starting near consensus, or actually starting at consensus, you can say, what is the time to reach the polarized state? You see here in this system, the consensus state is not a fixed point of the dynamics anymore, because if everybody, say, goes to the plus state, some people are still listening to CNN news and might get influenced from them. So now consensus is no longer a fixed point. So what I call the consensus time is the time to reach consensus starting from some initial composition, but it's not a fixed point of the dynamics. So this system is always continuously evolving, and we can ask for these 2 different timescales. And it turns out they're quite different. So now I'm actually going to be a little bit cruel and talk about some of the mathematics that goes on underneath this. So for the exit probability, so here Y is the fraction of people, say, who listen to CNN or Fox. And how does, again, this backward Kolmogorov equation for the exit probability has its same meaning as I showed earlier on, which is that if I start with a composition Y, So capital R is a probability of like hopping to the right. So again, in my one-dimensional space of opinions, I have only plus and minus if I start at position Y. So the probability R of Y, which I'll compute in a moment, I go over here, and then I have the exit probability starting with this new state where Y has been increased by 1, or I could step one step to the left, and I have the exit probability with moving one step to the left. And then with the complementary probability, I don't do anything because I picked, I picked someone who agreed with me, and then there's no evolution in the population. So this is the equation that we have to solve. And it turns out that if you go to the continuous limit, it looks very simple. It's, this is like a diffusion term, this is a convection term, and this is the equation that you have to solve with some very simple conditions for what are these velocities, the rate of going to the left or to the right, and the fluctuations. I mean, this is all like very standard technology, so I'm not belaboring it, but if you want more details, I'm happy to provide them. But anyways, this equation, it's like a standard thing in stochastic processes, how you write down the solutions to the equation. So here is the solution to the equation. And so we can find the exit probability as a function of the initial composition of the population. And then the other thing is that one can also compute the polarization time, how long is it, or the consensus time. That is, how long does it take to reach consensus starting from some initial state. And so here I've written the equation almost the same as before. You see, it looks almost the same as we had in the previous slide, but notice there's an extra delta t because I'm starting at position Y. So if I make a step to the right, you're right. No, that's my right. Sorry. So I make a step to the right. And so I have the same process starting at Y plus dy, but I wasted the time dt, the time for a microscopic event to get here. And so the time is just the probability times the time at the new point plus the time I wasted making that single step. And so if you work through the mathematics of this in the continuous limit, you end up with what's called the Poisson equation of electrostatics. And this equation you can also do some sort of standard stochastic process stuff and solve it. And so one can write down a formal equation for the consensus time and the polarization time. So after a bunch of work, this is, and let me not belabor this, it's just kind of cool because it looks like it's diffusion and a logarithmic potential. But here's the main results. First of all, the exit probability as a function of composition. So the straight line is what just comes out of good old voter model, where there's proportional rule and there's this underlying martingale. And so if you have 2/3 plus, you'll end up 2/3 of the time in the plus state. In this particular case, one has a sort of anti-sigmoidal shape. And this is indicative of that you're essentially living in a potential well. So the point is that because Fox News is over here and CNN is over here, and they're all yelling at you to do the opposite thing. And if I start very close to CNN over here, I hear Fox News yelling at me or CNN yelling at me, I don't know what to do. So I kind of just get moved to the center. And then you exit starting from the center. So the point here is that if you're very close to, okay, bye. If you start with very close to like one of the extremes here, you have only 10% or 5% of the population in the plus state. But because of this sort of noise, cacophony that's like telling people, to do opposite things, and most people just don't know what to do, they just fall into the center. And that's why this curve is this anti-sigmoidal shape. And as you increase.
Can I just ask you something?
Yeah, sure.
No, it's because I missed something, because you said before that consensus was not a steady state.
That's
right. Transient, right?
Mm-hmm.
So this is trying to reach that transient.
That's
state?
right. Exactly. This is the problem.
Okay.
This is the problem. Reaching that transient state is a function of composition.
Okay. Okay.
And here, notice there's this number alpha here, which is characterizing how strong the bias is. And that's related to P, which is this propensity for listening to news source compared to listening to your neighbor. And then the consensus time, also, this is the good old voter model consensus time. The mean for limit T scales linearly with N. And as you increase the strength of the noise of the two competing news sources, this grows faster than linear. And we have a theory that allows us to find out how this consensus time depends on on n. And the main point is that it's growing faster than linear n, which seems to say that it's harder to reach consensus. And the last part of this talk is now we can do something a little bit more realistic, which is now in the United States, it's like we're not like a complete graph. I have never talked to anybody in Kansas, and the chance I will is pretty small, or North Dakota or South Dakota. So now a more realistic version of this is that we have our, liberal coastal elites, we have our conservative, well, I guess they're over here, and they watch CNN News, and then we have the people in the heartland of the US who are conservative, they listen to Fox News, and there's not much connection between them. And so a more refined model is you say you have these two complete graphs of people who live in their own echo chambers. There's weak connections between the echo chambers. And then if you're on this side, you watch CNN and you never watch Fox News. In the previous model, there was a chance you could watch both CNN and Fox News. And now we can ask, so what happens in this case? This case turns out to be.
Sorry, but then there's interaction,
Yes.
Interaction between neighbors from the different clusters?
Yeah, so there is,
Okay.
so these dotted lines here are meant to represent the weak connections among different people, and is characterized by this exponent beta, which says what fraction of your neighbors in the opposite echo chamber do you actually happen to talk
Be
to?
able to interact.
Right,
Okay.
and so like if this was linear in n, then this would be like very well connected and back to our old model. But if beta is less than one, then it's poorly connected, and then it's interesting. Anyway, so the main point here is that this model cannot be solved, but like here is a picture of the opinion trajectory as a function of time of the two different enclaves. And so here are the Fox News people, and sometimes they might even get to 40%. They might become liberal, but they're kind of stuck around the conservative base, and similarly for the other side. So there's very little mixing of the opinions as a function of time. And then one can also numerically, we have a theory that allows us to estimate the consensus time and the polarization time. And the main point here is that, here we're talking about weakly connected, echo chambers. So the exponent of beta should be less than 1. And then the consensus time in general scales faster than linear in the population size, which is what we see in the data. But the polarization time, which is the time to start where, say, everybody is in agreement, but then the effect of Fox News and CNN is to make the CNN cluster become leftist, Fox News become rightist. The time that it takes to reach a 50-50 state is always linear in n. So very quickly, if you start with consensus, you're going to be driven to polarization. And if you're in a polarized state, the chance of reaching consensus, so the time to reach a consensus state becomes very long. So, it's as you would expect that these forces are trying to drive the system away from consensus.
Sorry, I understood earlier that the polarized state was the long time steady state, but now it's not.
Well, again, it depends on the relative, the connectivity between the two cliques and how you are connected to the news sources. But if you're very weakly connected among them, you can reach a state where everybody is in agreement, but then very slowly you'll do some very slow relaxation to a polarized state, and you'll stay there for a long time. And then, so I'm sorry, I'm not answering your question. Maybe ask it again.
No, I'm just wondering, because you're saying that it's possible to get out of the polarized state,
right,
and then maybe go back again to polarized. I just thought that the long time behavior of the system was polarized state. So when you go into the polarized state, you cannot get out of it.
No, you can't get out of it. It's just that it's very hard to get out of it because there's an effective potential well that tries to keep you there.
Yeah.
So it's almost like if you think about a random walk in a potential well, then it fluctuates around the potential well. But if there was absorbing points at far away, eventually if you reach the absorbing point, you'll stay there. But it's just most of the time you spend at the bottom of the well and the very rare fluctuations of the potential well. All right, well, anyway, so that's the end of my story. So let me just sort of make some comments at the end here. So I hope I've given you a sense, and I really didn't do justice to the voter model because I didn't do any detailed solution, but the voter model is, first of all, incredibly simple to define. and it has rich dynamics, and it's easy to see like how you might extend it to like reasonable social situations, more states, more different types of interactions. There's all kinds of possibilities there. But still, the voter model is missing a lot. And one thing, as I mentioned at the beginning, was this notion of heterogeneity. Everybody's different, and so how do we include that in a simple voter model? I've done it with one paper, but I think it was very naive. But the basic idea was that the rate at which you change opinion is just you have your own rate of changing opinion. But then I think what's even more important is the notion of irrational. I mean, we hear from economics about the notion of a homo economist, like the rational agent. But there's lots of research that shows that people just are simply not rational. They don't work in their best interest. And then there's this notion of discordancy, which is that I live with some self-contradictions. We all live with some self-contradictions. How do we include that in the framework of a simple model? And then I spent some time talking about models of opinion diversity. And so I hope I've given you a sense that, yes, it is easy to construct minimalist models, appealing models you say, oh, I should simulate that or see what happens. But I mean, it has some downsides to it, which is one is that everything that we've discussed so far, you see there's no data. Well, there was one data set, two data sets, the Canadian elections and the number of parties in Parliament. But in terms of like really having a calibrated model that you like test against data, this is all like at the level of game playing. And so what kind of questions can we ask, and what kind of connection can we make between models and data? And the other feature is that a number of people in my area have tried to use this as predictive models, which I think is really dangerous. And so I just think that's an open question. Is predictability a goal or even something that's possible? And that's it. That's it.